Hello and welcome once again to our tutorial class presented to you by O3 Schools JAMB app. The only application you require while preparing for your JAMB. It gives you a bright array of activities, quizzes, information, as well as your past questions with explanations on how the questions were solved, and it costs just 2,500 naira to activate this app. So once you download this app on your Android phone or your Windows PC, you can simply follow the processes for activation and activate your application. And once you do, you can gain access to the wide range of opportunities offered you by this app. There's no reason to be scared or worried about the process. Simply follow the process exactly as it is outlined in the app, and the app shall be activated instantly. So, with that in mind, let's go back to this class. And in this particular class, we shall be looking at cells and internal resistance. So cells. What is a cell? A cell is simply a device used to produce direct current through the process of electrolysis. Most cells, they all use electrolysis and to produce current, which is direct current, DC. There are two types of current: alternating current and direct current. The one provided by the power station or your generator is alternating current, while that provided by a simple battery is direct current. So for every cell, some of the things they must have include the electrodes and the electrolytes. Every single cell, no matter the type or nature, must have electrodes and electrolytes. And the electrodes are of two types: the anode and the cathode. The anode is the positive electrode, while the cathode is the negative electrode. Your electrolyte, on the other hand, is usually a molten solution of some salt. So typically, there are several types of cells. There is the primary cell and the secondary cell. Secondary cells are also known as accumulators. Now you may say, what is the difference between these two types of cells? Your primary cells cannot be recharged. That is their basic defining property. A primary cell cannot be recharged, but a secondary cell can be recharged. Now, some of us oftentimes using our batteries in our remotes or some of our devices, and we're like, it has not died yet, or when it has died, we can sort of reuse it. No matter what you try to do to such battery, it shall never go back to peak optimum condition as it was in the first time you put it in, because it is a primary cell. But the battery in your phones, for example, can actually always be charged back to 100%, and then it runs for the same duration as it did the very first time you got that phone and that battery was 100%. So that's the basic difference. Primary cells cannot be completely recharged, while secondary cells can be recharged. And there are several types of primary cells. There's the Daniell cell, and there's also the Leclanché cell. While for secondary cells, we have the lead acid accumulator, and we also have the nickel ion accumulator. This is usually known as the knife accumulator. So So that's it. Lead acid accumulator, nickel ion accumulator. While for the primary cell, there's Daniel cell, the Cantor cell, there's dry and wet type. There are some defects of the primary cells which are not undergone by the secondary cells. And these defects or issues are polarization and local action. Now, polarization is the deposition of hydrogen bubbles at the copper plate of the primary cell, while local action is a form of self-discharge, which makes the cell to keep on discharging current even when not in use, and is usually caused by the presence of impurities in the cell. So these are two defects that affect your primary cells, but which do not affect the secondary cell in any way or manner. And those are our types of cells. Now, however, from what we must know about Ohm's law, which states that the current produced in a mechanical conductor is proportional to the voltage, we know from Ohm's law that V must be equal to IR. However, this is not necessarily a stable and always used because we use VA as potential difference. What then happens if this cell has internal resistance? What is internal resistance? Say I'm trying or I have the ability to produce 10 volts. But in trying to get this 10 volts out, I have to first of all waste 2 volts because of opposition within me. That's what internal resistance has to deal with. Internal resistance is opposition to the flow of current being provided within the cell itself. So before it can even get to the external resistor which you oppose, it already has to deal with a certain internal resistance intrinsic to the cell. Therefore, as a result, we can now say that E must be equals to V plus small v. This big V here has to refer to the terminal voltage, the potential difference that is able to come out, while small v here refers to the lost voltage or the potential drop, the one that could not come out. Therefore, we now go back to our typical Ohm's law. Across the external resistor, we must experience this big V, but across the internal resistor is where this small voltage gets lost. So this will be I times small r, such that E becomes equal to I into r plus r, and therefore I must be equals to E over r plus r. See? One more time. E here represents the electromotive force of the cell. Capital letter V is the terminal voltage or the potential difference of the cell. Small v is the lost voltage or the potential drop. Small r here represents internal resistance, while capital letter R is the external resistance. So if this was my circuit, my e.m.f is here, and there will be an internal resistance intrinsic to the cell. Then this is the current, and this is the external resistor. Therefore, looking at these analogous formulas, we must know that big V equals to I big R, while small v equals to I small r. And with that in mind, there's something else we may now look at, which is the efficiency of the cell. And as we are aware, efficiency is always output over input. So the efficiency of this cell can be gotten based on what is the output of this cell. The output of this cell is terminal voltage, the potential difference that goes out. That's big V, while the input of the cell is everything it had to offer, which was the e.m.f. So big V is I big R Why E equals to I into R plus R. I cancels I, and therefore the efficiency of the cell will be R over R plus R. And you always express efficiency as a form of percentage. Do you see? This is a basic thing we need to know about our cell. And with this, and with our knowledge of Ohm's law from previous lessons, we can actually proceed into solving several examples in this topic. So, let's see. And at this point, you have to open your O3 Schools JAMB app and then assess the questions we want to solve. All right, so our first question will be from the year 2002, question number 38. 2002, question 38. An electric cell with nominal voltage E has a resistance of 3 ohms connected across it. Connected across this EMF is resistance of 3 ohms. If the voltage falls to 0.6 E, now once you connect this, the voltage then drops to 0.6 E. Means initially E was supposed to come out, but once I connect my resistance, what I then get coming out is 0.6 E. We're then asked, what is the internal resistance of this cell? Now, the question becomes, what can we do based on what I have? I can say E equals to big V plus small v, and E equals 0.6 E plus small v. Small v must be E minus 0.6 E, which will be 0.4 E. However, having done this, question now becomes, okay, how has this helped me? Do I know what to do next? Then I ask myself, going back to my big V and R, I know that I equals to big V over R. Big V is 0.6 E and R is 3 ohms. 0.6 over 3 gives me 0.2 E amperes. So my current is 0.2 E amperes. And then if I'm now going to analyze using my lost voltage, which is small v equals IR. Small v, as I can see here, is given by 0.4 E. The current is the same as I've gotten previously, 0.2 E times small r over 0.2 E over 0.2 E. So this cancels this, E cancels E, and therefore R equals to 0.4 over 0.2, giving a value of 2 ohms, and that is option C. So as you can see, when you have a physics question, if you do not know what to do what you know, and as you progress, you are going to realize that the steps will actually appear for you. All right, example 2, and this time we are going to question number 31 from the year 2001 of our O3 Schools JAMB app. Now this question says, a cell can supply currents of 0.4 ampere and 0.2 ampere through a 4 ohms and 10 ohms resistors respectively. That means the current is 0.4 ampere when the resistor is 4 ohms. That will respectively means, and the current is 0.2 amperes when the resistance is 10 ohms. We are then asked to find the internal resistance of this cell. What do we do? One more time, bit of analysis. I know that EMF E must be equals to I into capital letter R plus small letter r. Okay, let's start with the first situation. All I know is that because it's the same cell, the EMF must be the same. So I don't need to have E1 and E2 because I know they are the same. I can simply say E equals, but then current is different. So I1 is 0.4 into capital R is 4. Then the internal resistance does not change since it's the same cell. So that, while for my next cell or for my next situation, the same EMF for my current is now 0.2 into capital R becomes 10 plus capital R. Now, if capital E equals this and capital E also equals this, then this must be equals to this because they are both E. So, how do I analyze? 0.4 times 4 gives you 1.6. 0.4 times R gives you 0.4 R. 0.2 times 10 gives you 2. 0.2 times R gives you 0.2 R. Collect like terms. 0.4 R minus 0.2 R equals 2 minus 1.6. Then 0.4 minus 0.2 gives you 0.2 R. 2 minus 1.6 gives you 0.4. So over 0.2 over 0.2 R equals 2 ohms. See, and if you check your JAMB app, that is option D. Very, very simple. And then we move on. In this case, we are going to now look at what if analysis type again. What if cells are connected in series and parallel, just like resistors and capacitors? Now, for a series connection of cells, we cannot have something like this. If this is E1, E2, and E3, then total EMF becomes E1 plus E2 plus E3. However, cells are polar. They have polarity, unlike resistors. What does that mean? A cell actually has a positive side and a negative side. A resistor, on the other hand, does not. That means it's actually possible to connect your cells wrongly. What does that mean? What if my cells now appear like this? Notice this guy is facing what appears to be the wrong direction. So what you simply do, you simply take one direction as positive, then the other as negative, meaning that my total EMF becomes E1, but instead of plus E2, plus is in the other direction, minus E2 plus E3. And you see, that's the difference for series connection of cells. If they all face the same point, then simply add. But if one of the cells seems to be facing a different direction from the others, make it negative, while the others remain positive. Those are the series combinations. Then if your cells and a parallel, if your cells are in parallel connection, then what do you do? In that case, this is E1, E2, E3. Then in that case, your total EMF is actually quite funny here. All you have to do is look at your cells and choose whichever one has a higher value. That means E2 will be E1 if E1 is greater than equal to E2 and E3. That means if you have three cells in parallel, your net EMF is simply gotten by choosing the greatest EMF and taking that as your answer. If, however, they are all equal, then it doesn't still matter. Pick any one, and that will be your answer. So if it's 10, 10, 10, your net EMF is 10. If it is 12, 10, 8, then your net EMF is 12. Just pick the greatest value you can pick. And if that is okay, we shall then move on to solving more questions. Okay, and this time going to our O3 Schools app. Let's go to the year 2000 and look at question number 35. The year 2000, question 35. Now, this question simply states, a radio is operated by 8 cells, each of EMF 2 volts, connected in series. If 2 of the cells are wrongly connected, the net EMF of the radio is. Now, each of the cells, E1 to 8, because I said there are 8 cells, they are all rated 2 volts and they are in series. But then 2 are wrongly connected, implies that they are facing the wrong direction. So if out of 8, 2 are wrongly connected, that means 6 are facing one direction and 2 facing the other direction. Therefore, I can simply say that my net EMF will be 2, which is the EMF of each of them, times these 6, which are facing the correct direction, minus 2, which is also the EMF of each, times these 2, which are facing the wrong direction. See, instead of adding it one by one, which you could also do, this is much faster. 2 times 6 is 12. 2 times 2 is 4. And 12 minus 4 gives you 8 volts. And so that will be our answer, option D. You see, it's that simple. And then moving on, 1999, question number 25. 4 cells, each of EMF 1.5 volts, and internal resistances of 4 ohms are connected in parallel. What is the net EMF and internal resistance of the combination? 4 cells, each of EMF 1.5 volts. As we are aware, if cells are in parallel, then as we said, so we pick the biggest value. But since all of them are 1.5 volts, then my net EMF must also be 1.5 volts. See, cells quite easy. However, the next thing we are being told is what is the net internal resistance as well. And each of them have internal resistance of 4 ohms. There's a tiny trick we need to remember. If resistors are connected in parallel, then the net EMF must be less than the EMF of the individual resistors. Now, in this question, I know that I have 4 resistors and each of them are 4 ohms. For them to be 4 ohms, that means that my net resistance after connecting in parallel must now be less than 4. And in my options, there's only one option which actually has a net resistance less than 4. That's D. You see, even without solving for that, I know D has to be my answer. But if we would like to see the solving, then you know that 1 over ROT, the formula for parallel connection, will be 1 over RO1 plus 1 over RO2 plus 1 over RO3 plus 1 over RO4 because there are 4 resistors. So 1 over ROT will be 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4. So 1 over ROT becomes, denominators are all the same. So you pick 1, 4. 1 plus 1, 2, plus 1, 3, plus 4, plus another 1 rather, that's 4. 4 cancels 4, that's 1 over 1. That means ROT equals 1 ohms. So you see, my answer becomes 1.5 volts, comma, 1 ohms. And that is option D. See, so our steps are quite simple. Next up, we shall be going to the year 2001. And in this year 2001, we want to solve question number 34. That will be our 5th question on this topic. And this one simply says, a cell of internal resistance R supplies current to a 6 ohms resistor. Internal resistance is R, external resistance is 6 ohms. And its efficiency is 75%. Efficiency of the cell is 75%. I'll define the value of R. As we stated in the lesson, we know the efficiency of a cell is external resistance over external resistance plus internal resistance. So that means 75%, which is 75 over 100, will be external resistance 6 over 6 plus R. That means 75 over 100, 0.75 equals to 6 over 6 plus R. And then we'll cross multiply. 0.75 into 6 plus R equals to 6. And 0.75 times 6, let's use our calculator. So 0.75 typing in times 6 will give you 4.5. 0.75 times R will give you 0.75 R equals to 6. Correct items. 0.75 R equals 6 minus 4.5. And 6 minus 4.5 is 1.5. So over 0.75 over 0.75. And if you divide, that simply gives you 2 ohms. And you see, our answer is option A. And this leads us to our next question, which is coming from the year 2000. Question number 40. The O3 Schools JAMB app. The year 2000, question 40. A cell of internal resistance 1 ohm supplies current to an external resistor of 3 ohms. We have to find the efficiency of the cell. As we just saw in the previous example, efficiency is external resistance over external plus internal resistance. The external is 3, external is 3 again, internal is 1. I'll give you 3 over 4. And as usual, we express efficiency as a percentage. So multiply by 100. And if you press that in your calculator, you get 75%. And just like that, we shall continue our analysis. The same year 2000, but now let's look at question number 33. 2000, question number 33. And in this question, we have a circuit as shown on your app. And we are simply told to find the values of V1 and V2 in this circuit. Now, to find it, all I have to remember is my EMF is 2 volts. My internal resistance, as shown in my diagram, is 1 ohm. Then I have 2 resistors in series there. And connecting them together, ROT is R1 plus R2 as usual. So that will be 3 plus 2, giving me 5 ohms. Therefore, now I can find my current. E equals to I into R plus R. So my E is 2, my I is unknown, my big R is 5, and the small one is 1. That means that 5 plus 1, 6I over 6 over 6. I equals 2 here 1, 2 to 6, 3. I is 1 over 3 ampere. And with this, to find the values of V1 and V2, just remember that V1 equals to IR1 and V2 equals IR2. So V1 shall be I, which is 1 over 3, times R1, which as you can see is 3 ohms. And if you do this, 3 cancels 3, V1 equals to 1 volt. Then for your V2, it will also be 1 over 3 for my I times R2, which is 2. So 1 times 2 gives you 2 over 3 volts. So my answer, obviously, being 1 volt and 2 over 3 volts, must be option D. And you see, you can proceed. These questions are very, very simple. Moving on, the year is now 1997, and we are looking at question number 30. Question 30 from the year 1997. This question tells us that 3 electric cells, each of EMF 1.5 volts and internal resistance 1 ohms, are connected in parallel across an external resistance of 2/3 ohms. 3 cells, each of EMF 1.5 volts. And what type of connection? A parallel connection. And as we know, for a parallel connection, my answer must be the biggest EMF. What's my biggest EMF here? They are all equal. So it must be 1.5 volts. Easy. However, they have internal resistance as well. And internal resistance are all 1 ohms. And because it's a parallel connection, I then know that that will be 1 over R1 plus 1 over R2 plus 1 over R3. Remember, we use small letter R because we are dealing with internal resistance. So that gives you 1 over 1 plus 1 over 1 plus 1 over 1. And as usual, because they all have the same denominator, pick one. 1 plus 1 is 2, 2 plus 1 is 3. Then turn around, ROT becomes equals to 1 over 3 ohms. So my internal resistance is 1 over 3. However, we're not quite done. We are told that the external resistance, big R, is 2 over 3 ohms. We want to find the current. So I equals to E over R plus R. My E is 1.5 volts. My capital letter R is 2 over 3. Small letter R is 1 over 3. So 1.5 over. Denominators are the same. 3. 2 plus 1, 3. And 3 over 3 is 1. So 1.5 over 1 gives 1.5 ampere. And see? Very, very simple. And we shall then take one last question, and we shall know that we have truly studied the topic of cells and their internal resistance. This last question comes from the year 1994. 1994. And this is question number 44 of that year. 1994, question number 44. Now, for this one, we are told, we are given a circuit, and we are told to calculate the current in the 12 ohm resistor if the cell has EMF of 12 volts and internal resistance of 1 ohm. Let's write down what we know. Internal resistance is 1 ohm. EMF is 12 volts. Now we have 2 resistors and they're connected in parallel. That means first thing I must do is find my net resistance. So the first one is 12, the next one is 6. If I find the LCM of 12 and 6, that will be 12. 12 into 12 is 1, 12 into 6 is 2. That implies that 1 plus 2 will be 3 over 12. 3 here, 1, 3 into 12 is 4. And when I flip both sides, that gives me 4 ohms. Now, if you recall, what you're looking for is to find the current in the 12 ohm resistor. Now, because these 2 resistors are in parallel, that implies that they are going to share the current or have the same voltage, which means all I truly have to find right now is, based on what I know, that E will be equals to I, which is the overall current which they will share, into ROT plus R. My E is 12, I is unknown, ROT is 4, and small r is 1. That gives me 12 equals to 4 plus 1 is 5i over 5 over 5. So if you use your calculator, 12 divided by 5 gives you 2.4 ampere. So now I know the overall current is 2.4 ampere, and that my 12 ohm resistor and my 6 ohm resistor are going to have to share this 2.4 ampere. The only question then becomes, how do they share it? There are several ways to solve this. We're going to adopt a simple method in which we don't have to use any new formula. So what do? We are aware that current in any device in a parallel connection is the voltage over that resistance. However, right now, I do not know this voltage. So what I have to do is find this my terminal voltage and divide by my resistance. How may I obtain this terminal voltage? I can obtain it by simply saying my lost voltage, small v, equals to I times small r. My I I've gotten is 2.4 and my small r is 1. So 2.4 times 1 is 2.4 volts. Therefore, E equals to big V plus small v. And big V will therefore be big E minus small v. So that will be 12 minus 2.4. 12 minus 2.4 gives you 9.6 volts. That means the current across the 12 ohm resistor will be 9.6 over 12. And using your calculator, 9.6 divided by 12 gives you 0.8 ampere. And that is option A. And so you see, simply follow your steps, follow the logic of the steps, and you shall always arrive at your answer. Now at this point, I want to thank you again for watching this video. If you know you've learned anything substantial from this video, please like and subscribe to this channel for more videos teaching you various topics and subjects, all courtesy of O3 School's JAMB app. And I put you the require should you truly want to succeed and do very well in your examination. My name is Athanasius. Thank you again for watching.